Okay, good morning. For this last session of our Midrasha, and it's my pleasure to welcome Diana
Ojeda-Aristizabal-Topological, yeah.
Who will talk from the University of Toronto, who will talk about topological partition relations for ordinals below omega to the omega.
Okay, thank you. So let's check the microphone. Is okay there? Yeah. All right. So we will talk about topological partition relations. So let me first start by reminding you what Ramsey's theorem says. So it says that whenever we have a coloring of pairs of naturals into finitely many colors, we can find some subset of the naturals, infinite, such that A is monochromatic. So if we stick the coloring to the pairs of A, this is constant. Okay, so now we want to think about variations of this theorem, where we endow the set that we are partitioning with some topology. So let's, so what do I mean? So let's introduce some topology. So what do I mean by that? So say we have two topological spaces. Say X is a subspace of Y. And we want to ask the same question. So given finite coloring of Y, given a finite coloring of Y, can we find some A subset of Y such that C restricted to the pairs of A is constant and A is homeomorphic to X. So this is homeomorphism. Okay, so in general here we are asking for a lot more, because we don't just want to say something about the cardinality of the monochromatic set, but also about its topological structure. So let's consider a very simple example. How should we do this? Yeah, here. So just a very simple example while we all wake up. So we just have X and Y are the same, and it's just omega plus 1. So omega plus 1 is the interval 0 omega with the ordered topology. So just a convergent sequence with its limit point. So let's see if at least for this simple topological space we could achieve this. So the best way to approach this is to just think about coloring first. So let's define a coloring on the pairs of omega plus 1, a 2 coloring by, so we say this pair gets color 1 if both X and Y are isolated and 0 otherwise. All right. So I should say that even though I'm introducing some topology on the set that I'm partitioning, I'm not restricting the colorings to be continuous. So these are just for any coloring. So here if we take any A subset of omega plus 1, which is homeomorphic to omega plus 1, well, it will look like this. It will be a convergent sequence. So for sure, I will have a pair of isolated points, which will get color 1, and I will also get the isolated point to the limit point together with the isolated point, yes, which we will get color 0. All right. So none of the two colors can be avoided by passing to a copy of omega plus 1. Okay. So now the next question is this the only obstruction? So basically, could we reduce any given finite coloring to this coloring? So let me, perhaps here we are being too ambitious to request a fully monochromatic set. So let me just introduce some notation. Which will be sort of like an easier task than what I stated at the beginning. So say we have two topological spaces. Okay, let's subspace of Y. And say we have two integers, let me call this L and N integers. So we will say, let me see, how did I? So we will say Y arrows X Ln. If any coloring of the pairs of Y, if for any coloring of the pairs of Y, we can find a copy of X which realizes at most n colors. Okay, so I'll write that down. So this means for any coloring of the pairs of Y in L colors, there is some A subset of X, subset of Y, such that the pairs of A realize at most n colors. All right, so if n is equal to 1, means that my set is monochromatic, but this is more general. So when I asked in relation to this example whether that was the only obstruction, the question is whether any coloring of the pairs of omega plus 1 can be reduced to two colors. All right. Okay, and the answer is yes. This is very easy to see. So we have omega plus 1. We can restrict, and we have, okay, so we are given some coloring of the pairs of omega plus 1, some finite coloring, and we can restrict it to the isolated points. So we get a copy of the naturals, and we can apply Ramsey's theorem to refine this infinite set so that all the pairs get some color L1. And then I can, so in that I can refine that infinite set further using the pigeonhole principle, such that all the pairs that are in that set together with the limit point get color L0. Okay, so really any finite coloring of the pairs of omega plus 1 reduces to this coloring here. All right, so let me give you another example. So for instance, let's see. Oh, sorry.
In your notation over here, you want A to be similar to X, right?
Oh, A similar to X. And what did I write?
In the notation.
Oh, yes. Yeah, realize at most 10 colors. Right, and A is similar to X. Isomorphic to X. Thank you. Yeah. Yeah. Was there? Yeah.
So what A would you pick in that?
In omega plus, here in this example, so it would be the infinite set that I obtained after applying Ramsey's theorem and the pigeonhole principle together with the limit point. It's not. It's going to have two colors, L0 and L1. So notice that here I'm saying any finite coloring can be reduced to a two coloring. Yeah. Yeah. So for sure we won't be able to get monochromatic. Yeah. All right. So here, I like to think about that as color blindness. I hadn't thought about it that way. Yeah, so these, so you said threes, where? Yeah. Yeah, so in that case, yeah, because you can just combine colors. Yeah. Exactly. Any other questions? That's all good. Okay, so let's think about another example. So say we are looking for copies of omega squared plus 1. That's my x, yeah. So this is the interval 0 omega squared with the order topology. And so I can see this as a subspace of the rationals with the order topology. Okay, so I can, in the rationals, I can find homeomorphic copies of any countable ordinal. So, okay, so here we have this subspace of that, and we want to ask the same question, or basically ask, can we reduce any finite coloring to some fixed number of colors? So let's do the same thing we did for omega plus 1. So let's think about a good coloring or a bad coloring, depending on how you think about it. Okay, so here it's useful to represent the rationals. So here we identify Q with fin. So these are the non-empty finite subsets of the naturals. Right? So okay, so fin is so if I identify a finite set with its characteristic function, then I can see fin as a subset of 2 to the n. And so the topology here is the subspace topology. So let me just make a drawing here because it will be useful later, just to see how the basic open neighborhoods look like. So here this is the complete binary tree, and I have some finite set. And so okay, its characteristic function will change between 0 and 1, but then eventually it will just be 0. So here 0 is to the right and 1 is to the left. So this is just the characteristic function. And an open neighborhood of S determined by some natural number will look like this. So we go to the tree, we go to a certain level n, and then we consider the cone above that. So let's write it out. So this would be the elements of fin that extend S restricted to n. So at all times, I'm identifying the finite set with its characteristic function. Okay. So this is so this right here would be this open neighborhood, USN. Right, no, not necessarily, but that's the one that I will use the most. That kind of neighborhoods are the ones that I will use the most. But it doesn't have to be, right? I could also consider some M here, and then the cone above M will determine another open neighborhood. Okay, so this is how it looks in the trees. I will think of it also drawn in the line. So say these are the naturals, and I have my finite set somewhere here, S. And so if I want to draw an element in the open neighborhood determined by n, so here in my drawing, n is bigger than the maximum of S, then an element in this open neighborhood will be S together with some other finite part that occurs after n. All right, so this is, so T, which is S together with this finite part that occurs after n, it's an element in the open neighborhood, in this open neighborhood around S. All right. Okay, so this is how we want to think about the rationals. And okay, and I promised you I was going to give you an interesting coloring. But first I have to define the oscillation map. So what is the oscillation map? So the oscillation map is defined on pairs of finite sets. So we want to define this oscillation map, but let me just make here an auxiliary definition. So say we have two elements of fin. So I'm going to define an equivalence relation on the symmetric difference. As follows. So if I have I and j in the symmetric difference, so okay, yeah. So for I and j in the symmetric difference, I will say that they are related if when I take the interval between I and j, this interval is completely contained in T, or it is completely contained in S. All right. Okay, so this is easier to see with a drawing. So again, let's say these are the naturals, and I have two finite sets. Oh yes.
Probably no one closed interval, because if one of them is in one if they're in the symmetric difference, then the edges are in two different sets, right?
And those will not be.
And so you probably want the open interval.
Yeah. Let's make a drawing and let's see.
Yeah.
Yeah. Okay. So okay. It's a yeah. So all right. So here. So I mean, you figure out.
Yeah,
basically, you figured out what this relation is doing. So okay. So say we have two finite sets, S and T, and I'm going to represent them in the naturals. So so here are all the naturals. So I will mark with a circle the naturals that are in S, and with an X the naturals that are in T. So let's do that. So I have some elements. Of course, they might intersect. Okay, so let's see. Let me just move this here. And okay, so we pass to the symmetric difference. So we forget about the, well, I made them intersect a little, so let's add more intersection. Okay, so that's the symmetric difference. I remove the intersection, and the equivalence classes of this relation are going to be this one, this one, this one, and this one. All right, so basically the blocks that you obtain when you see both of them. So they oscillate.
What is ST for? Why did you put there ST?
Because the relation depends on ST. So
Oh, so it's not an abbreviation of a name
like a standard. Stable. Oh yes, which by the way I should which by the way, yeah, I should say this is a definition due to stable. Yeah, that's true. I never saw the ST as abbreviating stable, but that's true. All right, so yeah, so the equivalence classes are just the blocks, and the oscillation is just counting those blocks. So the oscillation is just counting the number of blocks. Yeah, exactly. So the oscillation is just I take the symmetric difference, mod out by this equivalence relation, and then I count how many blocks I get. So that's the oscillation map. Now let's go back to this example, and let's maybe I shouldn't. Maybe let me just move this. Yeah. So let's go back to that example. Yeah. All right. And let's see what happens with the oscillation map when we are in a copy of omega squared plus 1. All right. So suppose A subset of Q, which we are all seeing it like thin. All right. So say we have this subset which is homeomorphic to omega squared plus 1. And so let's see what happens with the oscillation map in A. All right, so here omega squared plus 1 is the interval 0 omega squared. So omega squared is a limit of limits, right? The omega times k's converge to omega squared. So omega squared is a limit of limits, and the omega, and these are limits, right, of isolated points. So omega squared is a limit of limits. All right, now, as I said, we are thinking of the rationals as thin. So my omega squared in the copy of omega squared plus 1 will be just a finite set. Okay, so this S, say, is the image of omega squared under that homeomorphism. And I'm going to see now how much oscillation I can get inside if I only consider pairs of A. All right, so this is omega squared. Now this is where this drawing, where I refer to this drawing again. So here, let's take an open neighborhood determined by some number that is bigger than the maximum of S. So I can find some, let's call it T0. So T0 is a limit point of A, which is in the open neighborhood of S determined by N. Now I can take another natural number and now consider this open neighborhood here determined by M. So I have S, and I'm considering this open neighborhood. So I can find some T1, let's say. So T1, so this is T0 here, T1. So I can find my T1 there. Now T0 and T1 are also limit themselves. So I can take, say, this open neighborhood of T0 and find some S0. So here, S0 is going to be like this. So S0 is in this open neighborhood of T0, right, determined by this integer. And I do the same with T1 because T1 is also a limit point. So yes. And this is T0 minus S. Yeah. Thank you. So, and we do the same with T1. So I take this open neighborhood, and then I find something here, which will be S1 minus T1. And so this is how my sets look like. Okay. So you can see already some oscillation going on there. So for instance, here the oscillation between S and T0 is 1. right? Because S is contained in T0, so when I remove the intersection, I just get one block. Then if I look at the oscillation between T0 and T1, so this is T0, T1, I remove the intersection and I get two blocks. And using T0 and T1, and using S0 and S1 and all the other, so for instance here, T1, this is T1, and S0, so I remove the intersection and I get oscillation 3. And now between these two, I remove the intersection and I get oscillation 4. All right, so this is, so that means that if we say color the rationals according to oscillation and assign different colors to oscillation 1, 2, 3, and 4, that will be a coloring that we will not be able to reduce in a copy of omega squared plus 1. And so we ask the same question. So here we had, I erased it, but before for omega plus 1, we had this bad coloring, and we said, is that the only obstruction? And we said, yes, we reduce any finite coloring to that two coloring, and we can also do that in this case. So, so in fact, this is a result of Baumgartner. Yeah. So for any number of colors, we can reduce to 4 colors in a copy of omega squared plus 1. All right. So, okay, so of course, so notice that in order to get the positive result for omega plus 1, we use Ramsey's theorem, we use the pigeonhole principle. So the Ramsey type theorem behind this result.
Aren't you saying a bit more? That it's not only the 4 columns, but that's a Ramsey basis?
Yeah. And we cannot do better.
Yeah.
Yeah.
That you showed.
Yeah, exactly.
That in fact, any coloring on the subspace will be the other way. I mean,
We'll reduce to this one.
Yeah,
Or
but reduce would be exactly the same.
Right.
A whole union of equivalence classes, coarser than that.
So yeah, so what happens here is that, so you are given an infinite coloring of the pairs of rationals, and you can find a copy of omega squared plus 1 that realizes only oscillations 1, 2, 3, and 4, and so that any two pairs with the same oscillation get the same color. Yeah. Exactly. Anyway, so for so to obtain the positive result here, we should apply some sort of Ramsey theorem, and the Ramsey theorem behind this is Hyman's theorem. Hyman's theorem. So I will not. Okay, and yeah. So I will not say much about how this is proved, but because we want to focus on another question. So the question we want to focus on is, so here we succeed in reducing any finite coloring to a 4 coloring in a copy of omega squared plus 1, but we are starting with a very rich topological space. So we may wonder, so is there some countable ordinal that would also do the trick? And so Baumgartner proved that the answer is yes. So he proved that there is some alpha countable such that for any number of colors, alpha arrows omega squared plus 1 pairs L4. All right. So the resulting ordinal from his proof is an ordinal like omega to the omega, 10 times. So that's the ordinal that results from his proof. But later, Claribet Piña, a former student of Estevo in Paris, she found an optimal value for the ordinal that could do this for us. And that ordinal, this is a big improvement. So the ordinal that she finds that works is omega to the omega to the omega. So for any number of colors, we have this. Yeah, and this is the best one. Yeah, and you cannot do better. So basically, the omega to the case don't work. Yeah, so this is really nice. And what is really crucial here is to find a good representation of countable ordinals using families of finite sets. Okay, so what we will do next, and this is what follows, is a joint work with William Weiss from the University of Toronto. So we want to study, how to phrase this, how to get copies of omega times n plus 1, say for m greater than or equal to 1. We already pretty much studied m equals 1. That's just the simple example at the beginning. How to get copies of omega times n plus 1, how much we can reduce the colorings, and so on. So, okay, so let's see where do we start? So where to start? We start by finding the sort of the Ramsey degree for pairs of these ordinals. So what is the Ramsey degree? So I will just define it for, let's say, for countable ordinals. Say for some countable ordinal, the Ramsey degree, let's write it like that, the Ramsey degree of alpha is the smallest d, so we're looking for finite Ramsey degree, the smallest d, such that for any finite number of colors, alpha arrows, alpha pairs LD. Okay. Let me see if so we want to see how much we can reduce a given finite coloring if we start with alpha itself. Okay, and so of course for a given alpha, this may or may not be defined. But we will calculate these Ramsey degrees for these for ordinals of this form. So we already actually started doing that because we found, so here we had any finite coloring can be reduced to a 2 coloring, and we saw a 2 coloring that cannot be reduced. So that means that we calculated the Ramsey degree of omega plus 1, and it is 2. All right. Okay, and we want to do the same for our family of ordinals here, omega times n plus 1. So let's do that. Of course.
You say that not every ordinal is a Ramsey.
Oh, no. Yeah, this might not be fine. Actually, you have to stay for sure below omega to the omega. Yeah. So in order for it to be defined. I just define it in general, just like that for simplicity, but it may or may not be defined. So, all right, now let me see what I can erase. So I think I'll erase this. All right, so let's say, so we want Ramsey degrees of these ordinals. Omega times n plus 1. Okay, so how do we do this? So say we are starting with, okay, so as I said, we want to see how much we can reduce a given coloring. So it might be that if we want to reduce to very few colors, even if we are looking for a copy of omega times 2 plus 1, we might have to start with more copies of omega times 2 plus 1. So I just write, in general, say we are working here in a S copies of omega plus 1. So I'll have my first copy, second copy, and so on. Okay, and we want to, okay, this is kind of an unfortunate setup because I wanted to show you here. So what did we do here to obtain the Ramsey degree of omega plus 1? So we identify two types of pairs that cannot be avoided in any copy of omega plus 1. So we want to do the same now when we are looking for copies, say, of omega times 2 plus 1. So let me see. So let's list those types. So type A will be two isolated points in the same copy of omega plus 1. So two isolated points in the same copy of omega plus 1. So this was the type that we saw for omega plus 1. Now there's this other type. So a limit and an isolated point also in the same copy. And now the moment where we want to look for more than one copy of omega plus 1, we will get all sorts of crossings between our copies. So for instance, we can have two limit points. So let's call that C, so two limits. And then I could also have two isolated points between different copies of omega plus 1. So two isolated points in different copies. Two isolated points in different copies. And I could also have a limited and isolated point in different copies. And I want to differentiate which one happens first. So let's say we have a limit first and then an isolated point in different copies. So this would be something like this. So a limit that happens earlier and then an isolated point afterwards. So this is E. And the other way around, so an isolated point and a limit point in different copies. Okay, so this would be so the isolated point comes first. So for instance, this. All right, so the idea of identifying these types is that we want to make sure that two pairs of the same type are as indistinguishable as possible. So for instance, if we focus on this type right here, so these are two isolated points in different copies of omega plus 1. So what we will have, so we will have one copy of omega plus 1 and another copy of omega plus 1. And so there are two possible types of crossings. Now I should say, so remember I'm focusing on the topology, but I'm talking about the first copy, the second copy, the third copy. So I'm giving some order, but basically if you have your copy of omega times s plus 1, then you fix an ordering of the copies. You say this is going to be my first, my second one, and so on. And then you fix an enumeration of the convergent sequences. All right? So, okay, so we have these two, and let's say this one occurs first. So I have two sorts of type D here. So it could be that my isolated point in the ith copy occurs before the isolated point in the jth copy, or the other way around. All right? And I will be able to distinguish that in a coloring. So we better split this type into two types. And in a given coloring, you may also distinguish which are the copies of omega plus 1 that are involved. So in order to really make any two elements with the same type indistinguishable, I should also refine this list of types, specifying where the points are coming from, which copies. So here I have in the same copy, so this is just parameterized by one integer. Same here. And now two limit points. This is one from the copy I, one from the copy j, and the same for these two, and for this one. Okay. And now here really this is sufficient refinement of the list of types, because we have the following result. So if we are given any coloring of omega times s plus 1, you can pass to an homomorphic copy of omega times s plus 1, where the coloring only depends on types. So I will write that down. So given a coloring of omega times s plus 1 into finitely many colors, we can find some A homeomorphic to omega times s plus 1, such that C restricted to the pairs of A depends only on types. Okay, so only on types, and by types I mean the refined list of types where you specify the copies of omega plus 1 that are involved. And this is exactly what we did for omega plus 1, right? We were given any coloring, only that for omega plus 1 you only have these two types, A and B. So we passed to a copy of omega plus 1 where the coloring depended only on types, and in omega plus 1 I only have two types, so that's it. Now, okay, so, and this is again, so these are like several applications of Ramsey's theorem and the pigeonhole principle. So, okay, so now so now this already gives us the Ramsey degree of, for instance, omega times 2 plus 1. So you just count the number of types in a copy of omega times 2 plus 1, and that is 9. And for instance, and in general, the Ramsey degree of omega times n plus 1 will be just a quadratic polynomial on M, which is to be expected because we are coloring pairs. So this is 2M plus 5M choose 2. Okay. All right. So that's the Ramsey degree, and now I want to. Okay. So let's actually write this down here. So, all right. So where do we go? Where do we go from here? We want to reduce the number of colors further. So let me just introduce some notation here. So let me just again define it for a countable ordinal, but I will focus on the omega times n plus 1. For alpha countable and a natural number. So gamma sub alpha of n will be the smallest ordinal. And let me just focus on countable ordinals. The smallest countable ordinal, such that let me just write it here. Such that every finite coloring, so for every finite number of colors, gamma, alpha, n arrows, alpha, Ln. So again, for a given alpha and a given value of n, these gamma alpha n may or may not exist. So let me so I will summarize our results in a table. So here we have n, we have gamma omega times 2 plus 1 of n, say gamma omega times 3 plus 1 of n, and let's say in general. Okay, and then I have to make sure I can go to 9. Okay, 9. So here, the way to read this table, so what do we want to put here? The smallest ordinal on which we can reduce any finite coloring of pairs to 9 colors in a copy of omega times 2 plus 1. So that's the Ramsey degree that we just found. So we know we have to put omega times 2 plus 1 here. Okay, and this one will happen afterwards. So the Ramsey degree of omega times 3 plus 1 is 21. Just the general form. Okay, so now we want to reduce. Further. We want to reduce the number of colors further. So what do we do? Right. Okay. So say we are given some coloring of the pairs of some omega times s plus 1 into finitely many colors. All right. I'll tell you what S is later. So if we are given this coloring, by the lemma, we may assume that this coloring depends only on this list of types. And so really what we have is colorings. What we have is a coloring of types, right? So we have, if we restrict our attention to the types in family A, we have a coloring dA, which is so my family of types A is just parameterized by a single integer. So this is really just a function from S to L, and the same for B. And for the families that are maybe not C but E, for instance, this family is parameterized by 2 integers. So this is just a coloring of pairs of elements of S. All right, so I have for types A and type B, I just have a coloring of S, and for the types indexed by 2 parameters, I have colorings of pairs of elements of S. So now, if S is big enough so that I can apply the pigeonhole principle twice and finite Ramsey theorem for pairs 5 times, yeah, 5 times and still end up with 2 copies of omega plus 1, then I can find, so if S is big enough, then we can find some copy of omega times 2 plus 1 and some colors LA, LB up to LF, such that D restricted to the pairs of A only realizes those colors. So if so that means, so what we've proved is that for any L, there exists some S such that omega times S plus 1 arrows omega times 2 plus 1 pairs L 7. So 7 families of types. And of course, this was not particular to 2, but clearly the number S will depend on 2. So I can write for any L and M, and this happens. So that means, so remember here, the ordinal that we want should work for any finite coloring. So if we want to reduce to 7 colors, for sure omega square will work. And actually, well, and we have a coloring that tells us that omega square is the ordinal that we are looking for, and that inside omega square we cannot go further. So we can at most reduce to 7 colors, and this is true in general for all the omega times n plus 1. Okay, so I will only maybe take 5 minutes, if it's okay, or like 4 minutes, to tell you. Excuse me. No. Oh yes, now I wasted my first minute. So okay, so now if we want to reduce the number of colors further, then things get slightly more complicated, but the idea is the same. So I told you with omega squared, this is as far as we can go. So we have to, so if we want to reduce the number of colors further, we have to go to bigger ordinals. So for instance, we should consider colorings of omega, for instance, of omega to the k plus 1. And this ordinal, we can represent it. So this is homeomorphic to the subsets of the naturals of size at most k. Again, seeing this as inside 2 to the n with the subspace topology. So now inside, so I should note that if we are past omega square, that means we have infinitely many copies of omega plus 1. So this notion of types here is not good anymore because we won't be able to get the lemma here. So what we do is we represent these bigger ordinals using these families of finite sets, introduce a notion of types in that context, and that allows us to say, okay, so that notion of types will be good in the sense that we will have a lemma like this. We can refine, so if we have a coloring of omega to the k plus 1, we will be able to pass to an homomorphic copy of omega to the k plus 1, where the coloring only depends on the types that we introduce in this context. And so, yeah, and so then doing an argument like analogous to this one, we can reduce the number of colors further. So at the end, what happens is that if we want to reduce to 4 colors, then we need to go to omega to the omega. And in fact, if I want to reduce to 6 colors already, we have to go to omega to the omega. So So this is all omega to the omega. And here by, I erased it already, but by Clarivet's result in omega to the omega to the omega, we can reduce to 3 colors. And here, so I don't have the time to illustrate this properly, but if I want to start with a countable ordinal, I cannot reduce to less than 3 colors. If you color with, say, oscillation mod 3, then that will be a 3 coloring on a countable ordinal that cannot be reduced. So here we don't have a countable ordinal that works. And let me see. Okay, and here, the moment where we have more than 2 copies of omega plus 1, we actually need to go to omega to the omega to reduce. Oh, sorry. Okay, so here, so if we have more than 2 copies of omega plus 1, then let me see. Then in the omega to the omega, as far as we can go so far is to reduce to 5 colors, and that's, as I said, just a result of having more than 2 copies of omega plus 1. Although I should say this is more like a wavy line, because it might be I just have to be smarter and do things better. So I should say this is less than or equal to omega to the omega, and I'm not sure if this will also work to reduce to 4 colors. Yeah, and so these are question marks, but probably the answer to these 2 will be the same. Okay, I think I'm done. Thank you.
So, other questions? Yeah, yes.
So if you have, okay, so you're thinking, so some lemma that would work for things beyond omega to the k plus 1, some notion of types. So there is something like that notion, although, so this must be, so I should say that, okay, so I said if we use this representation, we get an equivalent here of this lemma, which is something that Clarivet does in her work without introducing this notion of types. It's just something that comes out of that. Now it's probable that so most likely hidden behind this result, or the result for omega to the let me just use here. So here in this result, there must be some notion of types that is what is getting this result. But as I said, so she doesn't use this language of types, so I haven't really put this into that context. But yeah, so here basically what you are doing is reducing any coloring to oscillation. Now, if you have 2 finite sets, you can, so 2 pairs of finite sets, you can differentiate them based on oscillation, but also on the sizes of the blocks, right? So there are many things that you can say about them. Maybe sometimes you have oscillation 2 with empty intersection, and sometimes with non-empty intersection. But somehow bypassing to this large ordinal, you are not able to distinguish length anymore. So then you get a coloring that only depends on oscillation. So probably in that context, there is also some notion of types that is doing the job. Yeah. Yeah. So here if we go down a column, or like up a column, up a column is increasing. Yes, and with alpha you have increasing here, yeah. That's true. Yes. Yeah. Thank you. Yeah. Yeah, so the rows are always increasing. So we know that what we should put here should be at least omega to the omega to the omega. Yeah. And David, it possibly, yeah. I haven't thought about model theory in a long time, but perhaps, yeah. Sounds like what kind of type, sorry? Yeah. Oh, that's right. Yes. So maybe in the back of my mind I had some model theory from my undergraduate years. But yeah, I should also think about it that way. And maybe I can use some tools from model theory, right, to obtain other results.
To play the role with exactly the type in the monadic second order theory of the ordinals.
Oh, okay. I might ask you more about that later. Yeah. Yeah, so between 7 and the Ramsey degree here, so you have also omega square here. So why is this the case? So no omega to the k is enough to reduce to 8 colors. So what we have is for every k, there is some number of colors such that omega times k plus 1 does not arrow omega times 2 plus 1 pairs L 8. So since we want to be able to reduce any finite coloring to 8 colors, this is saying that no omega times k is enough. Yes. So here, right. So here, yes. So if we go here to what was, I forget what. Now it's too hard to calculate that. 21. Yeah. So it happens the same. So you really need to go all the way to omega square to go to the next level.
Okay, so let's thank the speaker again. And we reconvene in, I would say, 12